Okay, so in yesterday's lecture, we solved this numerical which was given as a homework, and this was the first numerical where we solved the problem, first assuming SCR to be ideal, and secondly SCR to be non-ideal. So we had written that if we are assuming SCR to be ideal in a numerical, then we have to replace it with a short circuit during the application of the firing pulse. So if the SCR is non-ideal, it will be replaced with a series combination of V on and R on, which represent the on-state voltage drop and on-state resistance of the SCR. So for the duration of the firing pulse, the SCR is replaced by a short circuit, otherwise replaced by V on series R on combination. And we solved this numerical yesterday. And then we discussed one important topic which is called as two transistor analogy of an SCR. Just there is some lag. Yeah, it was this. Yeah. So we have visualized the 4-layer structure of an SCR as a combination of two BJTs, namely Q1 and Q2. Q1 is PNP and Q2 is NPN. So the top 3 layers form the PNP transistor comprising of P1, N1, P2 with terminals emitter, base and collector, and the 3 layers from bottom, they represent NPN transistor Q2 with N2, P2 and N1 representing the emitter, base and collector of NPN transistor, and based on the connections between the base of Q1, collector of Q2 and between collector of Q1 and base of Q2, and considering the current directions which are standard for NPN and PNP transistors and all the current relationships and the basic mathematical expressions for the currents in a transistor, we ultimately came to the conclusion in equation number 17, wherein we established the relationship between the device current IA, the gate current IG, and the common base configuration current gains of transistors Q1 and Q2. So here we see that IA is equal to alpha 2 into gate current IG upon 1 minus alpha 1 plus alpha 2. So equation number 17 says that IA will tend to infinity when alpha 1 plus alpha 2 will tend to unity. Now this is theoretically not possible for the device current to become infinity, but we can say yes, a very large value. So we at the end of the lecture mentioned that there is a phenomenon called as regenerative feedback action occurring inside an SCR. So even we can see here in this two transistor analogy, the rightmost part, we can see that the base current of the transistor Q1, it becomes the collector current of the transistor Q2. Similarly, the collector current of Q1 also aids to the base current of Q2. So this kind of a closed loop or a feedback action ultimately leads to latching of an SCR. So we told that, not we told in the sense, we already mentioned that SCR is never latched in the absence of gate drive. So a practical approach to latching an SCR is to never increase the anode to cathode voltage beyond the datasheet rating of the SCR, that is breakover voltage. So VAK exceeding VBO is never the practical method for latching an SCR. Rather we told that SCR is always fired at values of VAK much lesser than VPO by applying increasing values of IG. So IG greater than 0 is the method of latching an SCR. So here we told that as we increase the value of IG, we see here that IB2 is equal to IG plus IC1. So IG increases, IB2 increases, IB2 increases, IC2 increases, and because IC2 is equal to IB1, IB1 increases and I1 increases. So increase in IG leads to increase in IB2, leads to increase in IC2, leads to increase in IB1, leads to increase in I1, and I1 is nothing but the anode current IA. This is called as regenerative feedback action. So I have written a comment here which we could not discuss because the session ended. So I have put the comments in my notes here. So we have told here that we know that SCR latches for all IA greater than or equal to IL, which is equation number 18. So we already have derived an expression for IA in equation 17, that is alpha 2 Ig upon 1 minus alpha 1 plus alpha 2. So when this particular fraction alpha 2 Ig upon 1 minus alpha 1 plus alpha 2, when this particular fraction exceeds IL, then SCR will latch. So we have told here, substituting the expression of IA from equation 17 in equation 18, we say that alpha 2 Ig upon 1 minus alpha 1 plus alpha 2 should be greater than or equal to latching current IL in order to latch the SCR. So I have written here, thus when we apply the gate drive, that is Ig greater than 0, and increase its value, regenerative feedback action starts, and when the value of LHS, that is left hand side expression, equates to IL, SCR will latch. So when the LHS expression it becomes equal to the latching current of SCR, which is a datasheet specification, SCR will latch. This was what our discussion ended with yesterday for the topic 2 transistor analogy of an SCR. So today we are going to discuss about two things, that is device ratings, and second is we will solve one more numerical on SCR. Now if you see till now we have solved three types of numericals in the chapter. The first type is numericals on SCR latching, and in that we had two categories. The first category of type 1 was that the input E in was of a DC nature, and we were expected to find if the SCR will latch for the given value of latching current IL and the given pulse duration. And a variation of this type was that E in was again DC, and here the latching current was given, and we were expected to find out the minimum pulse width required to ensure latching. And the second category in type 1, that is the numericals on SCR latching, we had input as AC. It was either a 110 volt 50 hertz supply or a 230 volt 50 hertz supply. Okay, and in this numericals, one more specification was given about the firing pulse, is that the firing angle was given. So if the input is of an AC nature, then such numericals need to specify what is the value of firing angle in addition to the pulse duration. And here also we are expected to find out whether the SCR will latch or not. So in numericals on SCR latching, if the input E in is DC, then what will be given in the numerical is the latching current of the SCR, and the pulse duration TP will be given, or TP will be given, E in is given, load is given, and we are expected to find out the minimum pulse width required. Or else E in is given, pulse width is also given, and we are expected to find out the limiting value of latching current, that the latching current should be less than or equal to the value of current attained by the load in the given duration of the pulse. And if the E in was AC. In that case, in addition to the duration of the pulse, firing pulse, also firing angle is to be given. The type 2 numericals which we solved were on the RC or transient model of an SCR, wherein we use the equation IA is equal to Cj2 into dVak by dt. So here either the junction capacitance of the reverse bias junction J2 was given, and we were expected to find the charging current or the capacitor current, and the dVak by dt rating was given. And today we are going to solve the third kind of numerical, but after we discuss the topic about device ratings. So the topic is device ratings, and when we say device, we actually mean power device. So we mean SCR, we mean any other member of thyristor family such as triac or GTO or static induction thyristor. By device, we also mean power BJT, power MOSFET, IGBT, or even static induction transistor. By device, we also mean diodes, power diodes. Okay, so general purpose power diodes, fast recovery power diodes, Schottky power diodes, SCRs, GTOs, triacs, static induction thyristors, power BJTs, power MOSFETs, IGBTs, and static induction transistors. So be it any member of any power device family, device ratings apply to all of them. So all of us know this important thing that when any engineer comes to the point of designing a circuit, what he does is that he uses standard mathematical equations to find out that what are the different voltages appearing across all the different nodes in a circuit, and what are the currents flowing through different branches in the circuit. So nodes and branches are what any circuit is made up of, and in between the different nodes what we have is different electronic components which can either be active or passive. If we say passive, then we may have resistors, inductors, or capacitors. When we say active, then it can be amplifying devices, we can have BJTs, we can have MOSFETs, or anything else. So whenever we design any circuit, we will know what are the maximum possible values of voltages appearing between the different nodes and the maximum possible currents which can flow through the different branches. That is why once we know what is the maximum voltage which can appear between two nodes in a circuit, or when I know that what is the maximum possible current which can flow through this branch, then it is possible for me to select an appropriate electronic component, may it be active, may it be passive. And all of you in third year must have heard about this thing, what is called as safety factor. So for example, if I know that I used a particular diode, okay, you take an example that I have some circuit here, okay, and there is some BJT which is connected here between, and then we have like this, and then I may have another circuit here, it may be bypassed here, right? So now this is first transistor, this is second transistor. So if I want to select this particular transistor, or if I select this transistor, On what basis I will select the transistors? I will first find out that what is the maximum possible voltage which can appear between these two nodes. Okay, so if this is node X and this is node Y, then I will be knowing clearly what is the maximum possible voltage which can appear between nodes X and Y. So once I know the value of Vxy max, now you know that X is nothing but the collector of transistor and you know that Y is the emitter, right? So Vxy max will naturally convert to VCE max, right? So if I know that the maximum possible value of Vxy is say 50 volts, then I will convert it, I will multiply it with a safety factor of 1.5 or 2, which comes out to be 75 volts or 100 volts. So if I know that the maximum possible voltage which can appear between nodes X and Y is 50 volts, and I know that between the two nodes X and Y the collector and emitter terminal are getting connected, then the VCE max rating of the device should be 1.5 or 2 times Vxy max. So I will choose a transistor whose VCEO rating is either 75 volts or 100 volts. Similarly, if there is some transistor I have to choose, and if I know that the current flowing through this branch is I max, and if I say that this I max is equal to 1.5 amperes, if I find out that I max is 1.5 amperes, I also know that this current I max is flowing through the collector terminal. So my I max is nothing but the maximum current flowing through the collector. So I must choose a transistor whose IC max rating is 1.5 times or 2 times. So I must choose a transistor whose IC max is equal to either 2.25 amperes or 3 amperes minimum. Got the point? So this is what a designer uses to choose components, that is maximum ratings of the device, right? So all of you being in third year, you must have gone through data sheets of diodes, and then BJTs, Zener diodes, MOSFETs, etc. But because we are discussing about power devices have a longer list of ratings which must be considered compulsorily and seriously before a power electronics engineer chooses a particular component for a particular application. So now we will discuss that what are the different device ratings which are important before we choose a power device for a particular application. So understand one thing, that when a circuit designer wants to select a power device to be used in a certain application, this selection is based on various important device ratings, because the designer knows the maximum possible voltages which may appear between the different nodes in the circuit, and also the maximum possible currents which can flow through the different branches of the circuit. Now understand students one thing, that since power devices are subjected to both AC and DC conditions, a power device has both RMS and average voltage ratings. Okay, so I'll write this point carefully. Okay, so a circuit designer knows the following two things about his design. First, the maximum possible voltage that can appear between not any two nodes, different nodes in the circuit, between different nodes in the circuit. And second thing which a designer knows is the maximum possible current that can flow through the different branches in the circuit. Okay, so maximum possible voltage that can appear between the different nodes and maximum possible current that can flow through the different branches in the circuit. And based on A, B above, the choice of components can be easily done. Now, second point which is unique to the branch of power electronics is this. Second, since power devices are subjected to both AC and DC supplies or conditions, they have two types of ratings, namely average so we will write down RMS first because RMS corresponds to AC. RMS and average. Okay, so since power devices are subjected to both AC and DC conditions, they have two types of ratings, namely RMS rating and average rating. Okay, now classification of device ratings. Device ratings are classified into three types, Okay. First is called as continuous rating. Second is called as repetitive ratings. REPETITIVE. And third is called as surge ratings. We will define all three of them: continuous ratings, repetitive ratings, and surge ratings. Continuous ratings, these ratings are related to the continuous working conditions of the device when subjected to AC or DC voltages. Technically, these ratings are expressed as AVG or RMS. Okay, so many times they are also called as, they are written as AVG or simply lowercase RMS. Okay, so related to continuous working conditions when subjected to AC or DC voltages or currents. Technically, okay, these ratings are expressed as AVG or RMS, also written as small AVG or small RMS. Okay, now we come to repetitive ratings. These ratings are considered when a power device is switched on off periodically at a very high rate. At a very high rate or frequency that is typically hundreds of kilohertz. Okay, so these ratings are considered when a power device is switched on off periodically at a very high frequency, typically hundreds of kilohertz. Now we come to surge ratings. These ratings indicate the maximum allowable voltage and or current, voltage and or current which can be handled by the device when they appear across or through them for a very short duration of time. Okay, so continuous ratings refer to continuous working conditions of the device when subjected to AC or DC. Usually these ratings are called as average or RMS ratings. If the power device is subjected to high frequency switching, then repetitive ratings are to be considered for design. And if a very high voltage or a very high current appears across or through the device for a very short duration of time, then surge ratings are to be considered. That is why I highlighted that these ratings indicate the maximum allowable voltage and or current which can be handled by the device when they appear across or through. Voltage appears across the device and current flows through the device. This is most important for a very short duration of time. This duration is only few microseconds. When I say very short, it actually specifically means few microseconds only. Okay, so we have seen what is the meaning of continuous ratings, repetitive ratings and surge ratings. Now we go in to see what is the nomenclature which is defined. Okay, so if we refer to any data sheet of any power device, it indicates the following three ratings based on standard nomenclature as explained below, right? So now we write down the data sheet of any power device mentions the different types of ratings that is one or more of the above three by using different standard alphabets and alphabetic combinations. Okay, so the data sheet of any power device mentions different types of ratings by using different standard alphabets and alphabetic combinations. So this is the table which tells us that which alphabet means what. Okay, alphabet and meaning. Okay, so we go from A to Z. Okay, alphabet A indicates anode. Usually the alphabet A is used for SCR. B is of two types. Okay, if it's B, then we have BO, it means break over. And if it's BR, it is reverse breakdown. So B basically means break. Then we have BO and BR. We don't have anything called as C. D comma D, small d comma capital D. We need to get forward bias and off state. And off state. F comma capital F indicates forward, simply forward. Small g capital G indicates gate terminal. So A indicates anode terminal. H comma capital H indicates holding current. L comma L will indicate latching current. M comma capital M indicates maximum allowable. Small p capital P will indicate peak. It can also indicate power sometimes. Okay, so if it is small p, it indicates peak. Capital P indicates power. Okay, so please make sure that this is small p and capital P. R. There are two variants of this. If R is used as the first alphabet, it indicates reverse. And if R is used as second alphabet, it indicates repetitive. Then we have S. The alphabet S indicates surge. T indicates threshold many times. Okay, indicates threshold. And you know that threshold is related to switching on a device or the turn on process or the process of taking any power device from the off state to the on state. Naturally, it means forward bias condition. So I can say in forward bias condition. Threshold, forward bias condition. And we have W, we have working conditions. Okay. So A is anode terminal, B is used for brake. We have two variants in this. If it is BO, it indicates breakover. If it is BR, it indicates reverse breakdown. Small d, capital D indicates forward bias, but the device is in off state. F comma F indicates forward. G comma G indicates gate terminal. H comma capital H indicates holding current. Small l comma capital L indicates latching current. M comma M indicates maximum allowable value. Small p indicates peak and capital P indicates power. Alphabet R, if it is used as a first alphabet or the only alphabet, it indicates reverse. But if it is used in the combination, if it is used in a combination, then second alphabet indicates repetitive. S indicates surge, T indicates threshold or forward biased, and W indicates working conditions. Okay. The same time, a revision of what you did in the first year, that is indication of instantaneous values, AC values, and DC values. Okay. So we have one more nomenclature. Indicating DC or any constant value and instantaneous value. Okay, there is something called as a DC or a constant value, and there is something called as instantaneous values. Okay, so our pure AC signal or the pure sine wave indicates a voltage which is having instantaneous values as a function. So in this we have the first thing, instantaneous value, values of voltage or current. We indicate using italics or something like this. Vs is equal to Vm sine omega t plus phi, or we have Is equal to Im sine omega t plus phi. So we see here that you know that Vm is constant and Im is also constant. So constant values are always indicated using no italics and capitals. Okay, so understand this thing, that DC and constant values are always indicated using uppercase and no italics. Uppercase and no italics. And instantaneous values are indicated using cursive. Cursive alphabets. Yeah. Now the second category is DC or constant values. Okay, so DC or constant values. Other categories are okay. Let me add them. DC or constant or maximum values or peak values. All of them are indicated by using uppercase. Okay. Uppercase alphabets. Okay. So for example, if I have a sine wave like this, omega t, and you know that this is instantaneous, so this is it, and right. So the instantaneous value of Vs is changing with respect to time, but the Vm value is constant. So in this system also, I will write instantaneous value as Vs of omega t, but I will write Vm as uppercase because Vm is constant and Vs of omega t is a function of omega t. Okay. Another example of a pulsating DC which has both non-zero average and a non-zero RMS value. Okay. So here also we can say it is a load voltage VL of omega t, and here it is output of a full wave rectifier. It's like this, and it goes like this. I know very well that this level is plus Vm, and this waveform, because it is not constant like DC, it has a non-zero average value, but at the same time, because it is changing, it is having an RMS value. So because this waveform is not constant, I made a mistake, because in this waveform the load voltage is not constant, so it has a non-zero RMS, and because it is unidirectional, it exists only above the x-axis, so it has a non-zero average value. So all of us know that in this the DC content is constant. We know that in this the DC content is indicated as, so in this particular waveform the DC content is constant, and we told that constant values are indicated with uppercase, so I use this thing VL, capital VL AVG, which is equal to 2 Vm upon pi, and again in this the RMS content is also constant, that is why I say it is VL of RMS, which is now equal to Vm upon root 2. So we already told that if the input source Vs is constant, then Vm is constant. So average and RMS content are also constants, right? So uppercase alphabets are used for DC or constant values or maximum or peak values. Okay, and here Vm is constant. In this waveform, the DC content is constant, RMS content is constant. Why do we say so? Because the DC content is equal to 2 into Vm upon pi. All three are constants. And RMS content is Vm upon root 2, which is again a constant. Okay. So here VLAVG is constant, VLRMS is constant. That is why although this waveform is continuously changing with respect to time, but because it is having a constant DC content and constant RMS content, provided Vm remains constant, that is why we indicate the average and RMS contents with uppercase. So VLAVG is written in uppercase using uppercase alphabets, and RMS is also indicated using uppercase alphabets. Okay, this is clear. So now I will write down some examples of different ratings which actually incorporate all this alphabetic system from A to W, and we will give the explanation tomorrow. Okay, ID, second IF, third VF, fourth IT, AVG, fifth is IT RMS, sixth IFGM, seventh is IFRM, eighth I subscript FSM, ninth IGT, 10th IR, 11th IRRM, 12th ITSM, 13th VDRM, 14th VRRM, 15th VGT, 16th VBO, 17th VRGM, 18th PG AVG, 19th I square T, 20, di by dt, and 21st is dv by dt. Okay, so these are some sample 21 different ratings. I do not think so that for any conventional MOSFET or BJT you must have ever seen so many ratings, because those devices usually are subjected to only AC voltages, that too low power, low voltage and low current. Power devices have a broad spectrum of operations, that is why. Okay, yeah, so we could not find time behind explaining the different device ratings and given examples, but in next class we will dedicate on only numericals, that is type 3 numericals. So amongst all these ratings, if we see, there are some ratings which are known to all of you, that is VGT, gate threshold voltage, IGT, gate threshold current, we have mentioned. Breakover voltage, we can also write down one more, VBR, reverse breakdown voltage, because this appeared in our IV characteristics. And we have dV by dt here. So when we discuss about high dV by dt triggering, we did mention about this thing.